Hi everybody. So this week is dedicated to the k-nearest neighbor learning algorithm, the first of a number of machine learning algorithms we're going to look at. The last video just kind of told you about the basics of kNN, showed you a bunch of code tricks in NumPy to compute distances, and then I sort of set you off on the task of creating your own k-nearest neighbor algorithm. It's your own function that could classify a point based on some training data. What we're working towards is assignment 2A, which I'll talk about a little bit here, but we'll probably talk about a lot more in the live class. So we'll leave that full discussion to the live class when you guys can ask questions and stuff. By the time you get to the end of our whole section on supervised classification, these assignments will be pretty straightforward. But the first time you do one of these assignments, the first time you get a data set and test it on test a machine learning algorithm on it, it can be a bit confusing about what it is you're supposed to do. But we'll get you there. Okay, so let me get up on the screen here. We're going to go over the second handout today. I called it Making kNN Better. But here it says kNN Problems, Solutions, and Tweaks. One of the things I'm going to ask you to do in the assignment is try different versions of the k-nearest neighbor algorithm. And you've already seen one way to create different versions of it, which is just to change the k. And sometimes that can help you deal with overfitting. So you can try a k of 1, a k of 3, a k of 5 on your data set and see which one leads to higher accuracy on the unseen testing data. But here I want to show you some other tricks that can be used to squeeze a better performance out of the k-nearest neighbor algorithm, and also some issues that the algorithm has. So the first one I want to talk about is the importance of normalizing data. There's some code that I gave you called norm.py, and if you run it, it produces a couple of graphs, and I want to show you those graphs here. So this is a data set where one of the two, so again, it's just 2 dimensions. By the way, I don't want you to think that you have to use 2 dimensions for k-nearest neighbor. It's just that when we visualize the data, we use 2 dimensions so that we can see it laid out on a flat graph. But real data sets are going to have way more than 2 dimensions, and you have to do you have to use all of them when you're doing k-nearest neighbor. So you have to do the Euclidean distance using 10 dimensions or 100 dimensions instead of just 2 dimensions. But in any case, our examples all contain 2 dimensions. So the thing about this data is we have 2 classes. One's marked red and one's marked green. And this is the point that we want to categorize. The black star is the point we want to categorize. So let's say k was 3. This would get categorized as green. It would belong with the green ones because you can see that these are its 3 nearest neighbors, and 2 of the 3 are green. But there's something weird about this data. So I've graphed it so that you can see the weirdness of it. Both the x and the y scale are the same. It's graphed from 0 to 100, so that you can see the distances accurately. If these scales were different, it would skew your visual impression of the distance. So it looks like those are the closest. But here's the thing about this data. One dimension ranges from 0 to 100. The other dimension ranges from, well, it's kind of hard to see, but it looks like from about 0 to 1. Let's take a look at the data. That's for class A and that's for class B. So you can see the data here. Oh, that's after it's been normalized. Sorry. Sorry, that's not the data. This is the data. So this is the raw data, A and B. So the data from the second dimension ranges between 0 and 1. But the first dimension, the values range between 0 and 100. And what that does is it skews the distance calculation in favor of that first dimension. So this first dimension is going to matter a lot more for the distance calculation. So if you think about it, the highest distance, the biggest distance in dimension 2 is 1. So the biggest y1 minus y2, the maximum is going to be 1. And when you square that, it equals 1. So the biggest distance in that dimension is 1. The biggest distance in dimension B that's possible in this data is 100. So x1 minus x2 could be as high as 100. And when you square that, it equals 10,000. So when you look at how that's going to work out, you're going to take the square root of distance is going up to 10,000 plus distance is going up to 1. Never mind. I won't use .sqrt. I will just raise it to the power of 0.5. Pretty close to 100. So the distance here, the 100, is dominating, because if I then change it so that it's got the maximum possible distance on dimension 1, but the minimum possible distance on dimension 2, the answer is still 100. So it's about 100 no matter what dimension 2 does. So if you have a big distance on this dimension, it's going to dominate anything on the second dimension, anything on the second feature. So the first feature dominates the second feature. And that's what's being shown in the first graph, the second graph here, the unnormalized data. What I can do though is I can normalize the data. And when you normalize the data, it means you scale down both the features into the same range. So typically you go from 0 to 1. So what I'm going to do is I'm going to leave the data where it is relative to one another. But on this dimension, see, I've scaled it down from 0 to 1. And this dimension has also been scaled from 0 to 1. And so that puts the two features on equal footing. Now their contributions to the distance calculation are going to be equal. And that totally changes the classification of the black star. So now, after you have normalized these two ranges, if you take the two nearest neighbors are clearly these two, which are both red, whereas down here it looked like the two nearest neighbors were the green ones. The third neighbor is actually probably this one. So probably with k equals 3, you've probably got a unanimous vote of red. Okay, this is the one thing that often makes a big difference in your data, depending on whether your features are all in the same range or whether they're skewed. So whether or not this is going to make a difference is going to depend on your data set. So if your data set has 10 features and they're all in the range 0 to 10, then normalizing is not going to make much of a difference. But if one of them or two of them have a range of up to 1,000, and the others all range from have a range of 10, normalizing the data will change things and will make a difference. So let's go back to the handout here. This is an example from there's a data set that I gave you, the online dating data set. It's a fake data set that was made up by one of the people that wrote one of the textbooks that I originally based this course on, and then since dropped. But it was a dating site, I guess, maybe an old style dating site where people ask questions and then you try to match people. So the idea is that we're trying to categorize people as good matches or poor matches or whatever. And we are looking at the distance between those individuals. So they ask them a bunch of questions, and here's two of the dimensions, two of the features that they would ask. One is the number of air miles you travel in a year. So you're trying to get a sense of how much the person travels. And the other one is the number of, I think it's the number of liters of ice cream you consume in a week. So it's obviously a little bit silly, but these are the answers. But this is an area where air miles is going to be in the thousands, and liters of ice cream is going to be in the small numbers. So we've got Sally and Sandy here, and we want to see how close they are together, how close these 2 points are together. And what I'm trying to show you here is that their difference in air miles is 25,000. The difference in ice cream is 1, but relative to one another, they're the same. This is Sally has half the air miles of Sandy, and Sandy eats half the ice cream of Sally. So when we do the distance calculation, 50,000 minus 25,000 and 1 minus 2, that's 625 million plus 1, square root of 625 million and 1, which is about 25,000. So again, this dimension totally dominates this dimension in the distance calculation. Okay, so if Sandy also ate 2 liters of ice cream per week, that would make her equal to Sally in this feature. It would give them an equal answer, but it would change this distance here to 0. This distance would become 0, and this would become 625 million. Square root of that is 25,000. So again, it almost doesn't matter what's going on over here. It's been rendered irrelevant by what's going on over here, by the size of the distances here. So normalize your data. Here is the equation for normalizing data. So what you do is you want to squeeze every feature down into the range 0 to 1. So for every feature, every column in your data set, you find the minimum. We know how to do that, right? We can find the minimum of every column all at once in a single command. Then you replace each value in the data with its normalized value. So that is the value minus the minimums, and you divide it by the range. So the range is the maximum value in each column minus the minimum value in each column. And this can literally be done. You can normalize your data in one line in NumPy. Okay, so you just replace this with an expression to get the minimum of each column. This is your original data set. This is an expression that gets you the minimum of each column. A single subtraction like this will broadcast that minimum across the columns. And then here you just need to find the maximum. Replace this with the maximum of each column divided by minus the minimum of each column. When we do that here, after normalizing it here, and here we're making an assumption that the range of air miles, so this can be a bit misleading because I'm assuming that the range of air miles, because I'm only showing 2 points here, but there might be 100 people in the database. So some people actually went 0 air miles, and some people ate 0 ice cream. And we're assuming that the range goes up to 2 and goes up to 50,000 for air miles to keep things simple. But it kind of looks like I've simply divided this column by 50,000 and divided this by 2. That's not this calculation. So you don't just divide by the maximum. You have to subtract off the minimum and divide by the range. So make sure you keep that in mind for a real data set. It's also in this data over here, I'm doing the same thing. I didn't want to give you the full equation. I wanted you to work it out for yourself. But here I'm dividing by 100 on dimension 0 because it ranges from 0 to 100. So this is the range. 100 is the maximum, 0 is the minimum. So I'm dividing by 100, but the minimum here could have been 10, and then the range would be 90, and I would have to subtract the minimum here. So the minimum is 0. So this is really, this is how I'm normalizing it. That minus 0, because 0 is the minimum value, divided by 100, which is the maximum, minus 0, which is the minimum. So that's the proper equation. So all the values minus the minimums divided by divided by the maximum minus the minimum. But again, I didn't want to give it all away, so I'm doing it that way. So don't just divide by the maximum when you are normalizing. That's not the correct way to normalize. But after we've normalized here, now the distance contribution is the same. The contribution is the same for both features. So 0.5 here, 0.5 there, becomes 0.25 plus 0.25. So the distance is 0.7. Now if Sally ate 2 liters per week, the distance between them would drop to 0.5. That's a 30% difference. So if this became 0, it would be 0.25, square root of 0.25, which is 0.5. So it would make a big relative difference. Whereas up here, if Sandy ate 2 liters per week, the difference would change by a factor of 0.00002 out of 25,000. So that makes a bigger difference, and it can often lead to a much better performance in your data by allowing all of the features to have equal weight. This does raise an idea, though. This brings up an idea, which is, what if after you've normalized, you sort of look in your data and look at what the features are and say, okay, I think feature 3 and 4 might be more important than the other features. So maybe we have a theory that the amount of ice cream you eat is much more makes you much more compatible than the amount of air miles, the relative amount of air miles. So after we've normalized, we could multiply this feature, this ice cream feature, by 2 or by 10 to make it worth more in the distance calculation. So you could actually experiment with weighting features differently to find the best weighting that seems to lead to the best performance on k-nearest neighbor. So that's just an idea. Okay, different values of k. So you should also experiment with different k values, and you try to use values of k that won't lead to ties. If you have 2 classes, you should choose an odd number. If you have 3 or more classes, it doesn't matter what number you choose. There could always be a tie. So it's worth keeping in mind that you need to break the ties, and how can you do that? Okay, so if you don't officially break the ties, then the tie breaking is going to be random. So for example, if you got k equals 7 and 3 classes, and 2 of the classes get 3 votes each and one of them gets 1 vote, you have a tie for the first place. When you go to sort, it's just going to essentially be random which class comes to the top and which class is the one that you choose as the label. So one way to break the tie, actually maybe let's use the second idea first. So if you've got k equals 7 and you've got a tie, maybe take a look at the 8th example. Maybe that'll break the tie. So let the 8th example vote. And then if there's still a tie, let the 9th example vote, and so on until the tie is broken. That's kind of a cool idea. So that kind of expand k. So start with k equal to whatever it is, and then if you get a tie, let the next neighbors vote until the tie is broken. Another way to do it is to use weighted voting. So use the inverse of the distance. So if a neighbor is 2 units away from a data point, it gets a vote worth 1/2, 1/2. If it's 4 units away, it would get a vote equal to 0.25, 1/4, and so on. So the closer the neighbor is, the more power it has, the more votes it has, basically. But you still might get ties, but they're going to be a lot less common if you do it that way. So that's kind of cool. Weighted voting by weighting by the distance. And yeah, watch out for overfitting. K equals 1 might get you good performance, but you might end up overfitting the data. So when you guys get your data for this assignment, you're going to split it into training and testing data, and you're going to do a bunch of runs to see how well it does. You're going to be giving it the training data with the labels, and then passing in the testing data one item at a time to see how it does. If you choose k equals 1, it might work well. Often it does for a lot of data sets, but sometimes expanding k to make it a bit bigger helps a lot. And we talked about that in the last one. Another thing that you can try, so again, in this assignment, I want you to try a few different versions on your data set, a few different versions of nearest neighbor. So you can try normalizing the data, you can try varying the k, you can try a different voting system for tie breaking like I showed above. Another thing you can do is, we've been using the Euclidean distance, which is the standard distance. If you want to find on a flat surface the distance in like kilometers or meters or whatever between two points, you use the Euclidean distance. That's the one that corresponds to real life shortest distance. It's not the only way to compute the distance though. So another one that you could use is Manhattan distance. And this might make some sense to try this. What Manhattan distance does is it doesn't do the squaring step. It just looks at the difference for every feature. So if feature 1 has a distance of 2 and feature 2 has a distance of 5, it just adds those distances together. It says the total distance is 7. So it's as if you had to, instead of, imagine you're in Manhattan, which is a part of New York that has a very grid-like structure. So you're here and you want to get here. In Manhattan or in any city with a square block structure, you can't go this way. You can't take the Euclidean distance. You have to go across city blocks like that. So you basically, if you're going from here to here, you have to travel all this distance and all that distance. So that's how Manhattan distance measures it. And sometimes it does a little bit better. So the way you do it is that you, for your training example, so your new data point is P, and your new data point has n values in it, P1 through Pn. The training example we're looking at has n values in it, T1 through Tn. We subtract T from P, so we subtract T1 from P1, T1 minus P1, T2 minus P2, T3 minus P3, and so on. These bars mean absolute value. So we have to watch out here because it might turn out T1 minus P1 might be -2, but we want our distances to be positive. So we use the absolute value. You can look that up. And then the sum here just means add them all up. So subtract one set of distances from the other. make sure that one set of features from the other, use absolute value. There's a function for it in NumPy and in Python to make them all positive, and then add them all up, and then you've got a different distance calculation that might lead to different performance. And then there's also the Minkowski distance, which is calculated like this. So when m equals, Minkowski distance is a generalization, okay? So when we're doing the Euclidean distance, let's go up here. We square the differences here and then take the square root. In Minkowski distance, you can put any number here. So let's say we go instead of squaring, we go to the power of 3. Then we would take the third root, which is raised to the power of 1 over 3. Or we could make this 5. We could raise it to the power of 5 and then take the fifth root. So you could try some of those as well. So Minkowski distance, when the exponent is 2, becomes Euclidean distance. When the exponent is 1, it becomes the Manhattan distance. But since we are sometimes using odd exponents, not even ones, we have to make sure that the result of each of these is going to be positive. So you have to, after you've raised it to the exponent, whatever it is, you have to take the absolute value. So that's what this complicated looking thing is saying. It's saying for each feature, subtract them, take the absolute value, raise them to some power m, add them all up, and then take the mth root. That's hard to say. Okay. So that's the Minkowski distance. So you can try that as well. All right. Finally, I just wanted to raise an issue with k-nearest neighbor, which is unbalanced data. So the example I give here is, suppose you have a training set that is all the news stories published in 2016, and you want to use that training set to train your learner to find news stories about earthquakes. Okay, so if you think about it, how many earthquake stories, if you've got all the news stories published in 2016, all 10 million of them, how many of those stories are going to be about earthquakes? You know, maybe 1,000, maybe 10,000. It depends what happened that year. But if there were not any huge earthquakes that year, even if there were big earthquakes, we're talking about all the news stories on all topics. The ratio is going to be really high of non-earthquake to earthquake. So I say maybe, let's say that for every earthquake story, there's 10,000 non-earthquake stories. Okay, so if you take a new, if you give that data to your nearest neighbor algorithm, and then you bring in a new story, let's say it is about an earthquake, the nearest 3 stories to that after you've encoded it, since there are so many non-earthquake stories, it's quite likely that the nearest 3 are going to be non-earthquake stories. Even though this is a story about an earthquake. So it's going to be really, really hard to find, to categorize positive in that situation. You're going to really default to the negative categorization. So one solution to that is so that's something to watch out for, and something that you should do. I think in the assignment I asked you to do some statistics on your class labels. Is there a really infrequent class label? And one that's really frequent? If so, then your training set is unbalanced, and k-nearest neighbor might not do as well as it otherwise could. Or you might get a misleadingly good result. So I'll explain what that means in a sec. But if you're unbalanced, one solution is to balance the training set. So when you read in your data, if you've got 1,000 to 1 or 100 to 1, just simply remove items from the overrepresented class. Or replace clusters of items with the same class label. But the easiest thing to do is to just trim it down. So let's say you've got 100 examples, 100 positive examples and 10,000 negative examples. You could randomly select 100 negative examples so you've got the same number, and then you could let it vote. Might work well, might hurt the performance. You don't know what's going to happen, but it's worth a try. Another solution is to weight the votes. So if you've got your one earthquake story and it lands here, and there's another earthquake story close, but then the rest of the neighborhood is non-earthquake stories. If you're closest to the earthquake story, using weighted voting might help here, because it'll give the earthquake story a lot more power when it's near to a new story coming in. So you use the same solution as before. There's also just an accuracy issue. So I would urge you really should look at how balanced your data set is, because let's say, again, there are 10,000 non-earthquake stories for every one earthquake story. So when you go to test, you're going to have a lot more non-earthquake stories in your data set. And if you get them all, if you just always say it's not about earthquakes, you're going to have a really high accuracy. Your accuracy is going to be 99.99%, because 99.99% of the time, it's not an earthquake story. So if you just always say, no, it's not an earthquake story, not an earthquake story, then you're going to get a really high accuracy. But that's not very useful in practice. So you look good on paper, but in practice, you're not doing the task. You're not actually identifying stories about earthquakes. So that's something that we will look at. I just wanted to flag that issue, and I want you to think about it when you're looking at your data set. If you find that your data set is unbalanced, you might want to balance it, because if it's very unbalanced, you're probably going to get a high accuracy, but it doesn't necessarily mean that your classifier is doing well. So you can achieve a high accuracy, but it's not going to be doing that well. So you could also look up, in future class, we're going to cover precision and recall, which are better ways of measuring classifier performance when you have unbalanced data. It looks at how, it's a better way of measuring how well you've actually done. How many of the earthquake stories in this data set have you managed to pick out, and how many did you pick out wrongly? That's basically what it measures. Okay, so what I'm going to ask you to do in the assignment, and I'm going to go over this in more detail. Oh yeah, I did want to show you this. I've got another example. Sorry, I should have shown you this before, but this is an example that's not in your code. This is for normalization. Hang on, I'm just trying to run it, but I think I have to spin up my drive first. I have a big external drive on my computer, which has a small solid-state drive. Sometimes it needs to spin up. Okay, so I have, just as an example here, I have the dating data that the Sally and Sandy example was drawn from. So I can say, and I have a function written which runs a k-nearest neighbor analysis on the data set, and the categorizations are weird. It's like, I would like this person in, I would not like this person, which is didn't like. I would like this person in small doses, so I like this person a little bit, or I would like this person in large doses. I want to spend a lot of time with this person. So you don't have to do this for your assignment, but I'm one by one for each example. After I split it up into training and testing data, I give the training data to my algorithm, and then I test. I have 200 testing points, and the number of errors was 49, so the accuracy is about 75.5%. Okay, I'm always splitting it the same way, so it's always the same accuracy. I can change the k. So if I change it to k equals 3, I get 1 point. I get 1 more point correct. I'm not doing any tie breaking here. I do a little bit better with k equals 7 and so on. But I guess it is a little bit different each time. I think I'm doing a different split. I'm getting the same same result each time. But I have a better version of the algorithm that normalizes the data. That normalizes the data first. And you can see, so if I do the k equals 1 step, all the accuracies were in the 70s. Normalizing this data does make a big difference. It gets me closer to a 90% accuracy on the unseen items. And then if I use k equals 3, I get 92% accuracy. K equals 5, 93.5. K equals 7, drops again. So maybe k equals 5 and normalized is the best way to go with this data. And that's using the Euclidean distance. Okay, so it does make a big difference in that particular data set, and depending on your data set, you may find that it makes a big difference. One of the things that you should do is you should look at the range of each feature and then print it out for yourself so you can see it. And if you see 1 or 2 features have a way different range than the others, then you should definitely try normalization, because it might make a big difference with your data. Sorry about that. That was a little bit out of order, but I did want to show you that example. Now, if we just go into, if we take a look at the assignment, so I'll go over this and answer all your questions, but basically what you're going to do in the live class, but basically what you're going to do for this part of the assignment, you're going to code your own nearest neighbor algorithm in Python using NumPy. Then you're going to, you can use the same data set that you used for assignment 1, and in assignment 1 you split the data into training and testing. So then what you're going to do is go through the testing data one item at a time and call your classify method And each time you call it, you give it the training set and the training labels and the new example, and then compare how it did come to the correct answer, and tally all that up, and then give a percentage of how many it got correct at the end. And you're going to use, it says here, 8 different versions of the k-nearest neighbor algorithms. And you should have 3 parameters, 3 things you change: the k-value, the distance metric, normalization, weighted voting, etc. And try different versions of the algorithm. And what I want to do is just go straight to, did I close it? Yeah, it looks like I did. There are some supporting materials online. One of them is a sample output. So when the program runs, here's an example of what part of the output could look like. So here I'm doing 1, 2, 3, 4, 5, 6. I'm doing 9 runs here, and I've got 3 different parameters that I'm changing. I'm changing the k value, so I run 135, 135, 135. I run the Euclidean distance in some of them and the Manhattan distance in others. And in the first 3 runs I did not normalize, and in the last runs I did normalize. So this is the, like I said, Wisconsin breast cancer data. And in each case I've done 5 runs where I split the training and the testing set differently each time. So after you read in your data, you have to put your whole program in a loop, do a different training and testing split each time, and then test it. And you'll see why we're doing that, because depending on how you split it, you may end up with quite a different result. So my last run was only 85% accuracy. My first run was 92% accuracy. So the runs differ quite a bit, and then you average those to try and get a general picture of how well this algorithm is doing. 5 runs is a low number, actually. If your code runs quickly, I would even go 50 runs or 100 runs if it runs fast. The more different training and testing splits you do, and then when you average it, the more data points you have when you average, the closer you get to kind of the real value. So it becomes a more realistic measure. With k-nearest neighbor, it's slow to categorize sometimes. So if you have big data sets, even doing 5 might take a very long time. You might find yourself having to leave your computer running overnight to generate your data, to generate your results. So this is kind of like the results. So when I run your code, it should do this. But it's not just about the code, it's also about a report. So from looking over this stuff, I can see that it does kind of look like k equals 5 was the best. And you should try more values than you output from your program. So try higher values of k, try a bunch of different combinations, but then output just a few that kind of illustrate the performance difference. Normalizing made a big difference here in this data set. It's a little bit hard to say beyond that. So if we look at these, they're all kind of the same result. Results between 94 and 96. Maybe this is the best one, but it's only 0.7 higher than the Euclidean distance one over here with k equals 3. So I would run this a few times and see, is this one consistently higher, or is that just a fluke of this run? And then I want you to do a discussion and say something about it. So I want you to, and this is the what data scientists do and machine learning people do on a day-to-day basis. They're tweaking their algorithms and trying to get the best performance that they can out of them. So that's what we're doing, is we're replicating some of the work of a real data scientist. The other thing I wanted you to look at is I'm asking you to write a report for this, and I've given you a report template that you can fill in. So later on in the assignment, it describes what goes into each part of the report. You're going to describe your data. You're going to give it a title and an author. You're going to describe it. And then you're going to tell me, for at least one run, you should describe the 3 parameters you varied for k-nearest neighbor. This is for part 2. So we're just doing part 1 right now. Next week we're going to look at decision trees, and you're going to compare these 2 algorithms and see how well they did. And then here I describe the run, k equals 1, Euclidean distance, k equals 5, Manhattan distance. So for all 8 or however many runs you did, I want the raw results here, and then the average here. And then a discussion where you, and I've got the part 1 and part 2 discussion here, but we're just looking at part 1 right now. And the last part is future work. So what should go in each of these sections is described in the assignment, but what I found is the first time I gave an assignment like this, I wasn't very happy with the way that people structured their reports, and it made it difficult for me to read and grade them. So you don't have to use this, but I would like you to at least look at it and consider using this this template as the template for your report. It'll make my life a lot easier if you're clear and things are laid out in a clear way. Okay, so read over the rest of the assignment, and we will discuss it in class, and bring any questions that you have to class. And I will see you in that class on Friday.